Welcome to this lecture on graph mining. So today we'll talk about PageRank. The motivation is to identify the most important nodes in a graph, either globally or relatively to some other nodes. This is useful, for instance, to retrieve some information, to recommend content, or to do some local clustering, that is to explore the neighborhood of a given node. And we'll focus on PageRank, which was, as you know, proposed by Google founders to rank web pages. And the idea was very simple. If you like to identify the most important pages, just browse the web at random, and then it's likely that you will visit more frequently the important pages. So we first talk about random walk in a graph, then we'll define and see the basic properties of PageRank. Then we talk about a personalized version of PageRank and by PageRank, which is a version adapted to bipartite graph. So the setting is the following. So we consider a graph with, let's say, n nodes and m edges. And as usual, we'll represent this graph by its adjacency matrix. So we'll assume this matrix is binary, so we don't account for weights, although everything can be extended to weighted graphs. And so we'll define D+, which is a vector of out degrees. So if you consider that particular node, for instance, its out degree is 1. Okay, there's just one outgoing edge. And this vector can be just very easily derived from the adjacency matrix by summing the rows. The same way, you have a D-, which will be the vector of in degrees, which is A transpose times 1. Okay, and now we'll walk in this graph, basically, okay, at random. So we'll follow the outgoing edges uniformly at random. So to be able to do that, we need to assume that they are outgoing edges, so we'll assume that the vector, all entries of the vectors D+ is positive. Okay, there's no sinks in this graph. Okay, which is the case here. So you start from a given node, then you move, follow one of the outgoing edges, and so on at random. So this defines what is known as a Markov chain. Okay, so we'll denote by x0 the original node, then x1 and so on, and so x2 and xt would be the state of the Markov chain at time t. And its dynamics are governed by what is known as the transition matrix P, which is just D minus 1A, where D is the diagonal matrix of out degrees. Okay, so Pij is simply the probability of moving from I to j. Okay, so Pij is just Aij, so you need an edge from I to j, and you select this edge uniformly at random among the outgoing edges from I. Okay, and it turns out that if you denote by P or pi t the distribution of xt, so the state of the Markov chain at time t, which is just one node. Now there is a simple expression to get the distribution at time t plus 1 from the distribution of time t, and it's simply left vector multiplication by the transition matrix. And we'll be interested in what happens in stationary regime. So when t tends to infinity, so let pi be the limit of pi t when t is large. And so this is actually the unique solution to the balance equation. The only condition is that your graph must be strongly connected and aperiodic, in the sense that the greatest common divisor of cycles is equal to 1. So under these conditions, you get a unique solution, and this is the limit of pi of t. So to compute this stationary distribution, you have to solve this equation. So basically you have to find the largest eigenvector, left eigenvector of P. Okay, since P is a stochastic matrix, you know that 1 is the right eigenvector for the eigenvalue 1. You need to find the left eigenvector. So there are solvers to do that, but an easy way is to use just what is known as a power iteration. You just start from an arbitrary vector, let's say uniform, and you iterate this left multiplication. And you get an approximate solution. The quality of the approximation actually depends on the number of iterations, and you can show that the convergence is geometric at a rate which is equal to the second largest eigenvalue of P. Okay, so this depends on the graph structure. The complexity here is k times m. So m is the number of edges, provided you store your adjacency matrix and the transition matrix P in a sparse format. And the cost in terms of memory is n. This is the size of the vector. Of course, you need also to store the graph, and so there is a fixed cost of m, the number of edges. So this is an example. So the score of importance, so this frequency of visits is represented by the colors. As you can see, there are 3 nodes here having a high score. And if you look at the structure of the graph, this is because you have a cycle here, and it's very hard to escape from this cycle. And actually, this is an issue, okay? And this is why you need to add some mechanism to solve this problem, and we'll come back to this with PageRank. Before that, so we need to look at the case of undirected graphs. So if the graph is undirected, so the adjacency matrix A is symmetric, and so the degree vector is A1, but it's also equal to A transpose 1. Okay, and in this case, it turns out that the stationary distribution is explicit, and it's very simple. It's just proportional to this degree vector. Okay, so let's show that. So remember that there is a unique solution to this equation, summing to 1. So we just need to prove that D transpose solve this equation. Then by normalization you get the stationary distribution. So what is D transpose P? Remember that P is D minus 1A, and this is 1 transpose. So you get 1 transpose A, which is D transpose. Okay. So this is an example of what you get for this graph. And as you can see, the frequency of visits is just proportional to the degree. In particular, you don't have to solve the balance equation. Okay, for undirected graph, you have the solution. You just take the vector of degrees and you normalize it. Okay. It's a very simple and deep result actually of concerning random walks in undirected graph. And again, this applies to weighted graphs as well. In this case, we replace the degrees by the weights of each node.